So, homework 2, as you know, due Monday, except you all know how 2 days late, so whatever, or 2 late days for assignments, so whatever, Wednesday-ish. Homework 3 will be out. We're gonna finish up this weekend. It's basically just getting polished now. I want to get that out early next week so that doesn't eat too much into your final project time. It'll probably be 2.5 weeks, possibly including the late day. A couple comments on comments. These I'll talk about all in detail. The final project proposals are due the 6th. That is, I think, next Friday, and then we'll give you feedback the Monday after. Pre-proposals are welcome and encouraged. Okay, so comments in homework. TFs have been grading homework 1. Comments in homework are awesome. All right, that's all I really need to say. If you tell us what you're thinking on a high level, even if you typed it wrong or there was just some minor error, we can give you partial credit if your comments show that you understand the material. All right, if all we have to go off is your code and your code is wrong, then we just assume that you didn't understand. But if you put comments in there, I'm trying to do this, and it's, there's just a misunderstanding of some library or something like that, then we can give you partial credit. And it makes grading easier. If you make our life easier, we are not above bribery. We're not allowed to take money, but we are allowed to give you extra credit for you did extra work that made our life happier. We'll make you happier too. Hooray! So, continue to comment well. We've seen there have been a few assignments that have really stood out in terms of Kendrick, right? Where's Kendrick? Yeah. I was like, he looks surprised, like, why are you calling me Kendrick? Kendrick is an excellent example of this. Really good comments. Very helpful. Made grading easier. Just perfect. And your future self will thank you or possibly curse you, depending on what you write. I have comments in code that's like, don't touch this. You understood it once. Don't touch this. You don't understand it anymore, and it's true. But in general, they're like, when you're doing your own work, even in the future, when you're productive members of society, unlike me, you'll write code. If you comment it, you'll find a few months later when you look at it, you're like, you'll look at the code and you'll be like, I do not understand. And you'll read the comments and you still won't understand. But you'll understand a little better, and eventually you'll add comments that time. I had code that I worked on that was 50 lines long. I worked on it for 3 years at a company, and eventually it had about 200 lines of comments, maybe 300. Each time I had to go in and fix another piece of hardware, had to adjust it for something, didn't understand the math I was doing, add another comment, add another comment. Eventually it was just like huge blocks of yellow text and like lines, like this is what we're doing. So, continue to do that. All right, OpenCL setup. I cloned the RC intro repository. I moved it to our own, the class repository. I also put in the missing lines in run tests that were left towards a homework exercise. So if you need to run it on Odyssey, you should be able to just run sbatch run test. And I think it's all set. You might need to do the source new modules thing. On your own machine, you should be able to run Python test.py if you have OpenCL installed. Yes?
Sorry. On the first slide, you just quickly went by. What's the date that we need to do the project outline?
The 6th. I'm going to talk all about final projects. There you go. Okay. On the next slide, too. So the 6th, so that is next Friday.
So not what it says online.
What does it say online? Oh, it says earlier, right? 2nd. Yeah, no. It's we're moving it to the 6th because we're a little bit behind. I'm encouraged, I encourage something earlier. So that the November 6th thing can just be a rubber stamp. But we'll talk about the details of this here for a while. If you're still looking for ideas, continue to post on Piazza, look at previous projects. If you're interested in some general thing and don't know what to do, send email to staff and we can maybe give you some ideas, or post on Piazza, say, I'd like to work in this area. What are some ideas? I'm going to talk now about what we need in the proposal and how that will lay out what's going to be done for the project. Okay, the project proposal should be about a page. It should list team members. I'm going to go over each of these, so don't worry too much about what I say here. But who's on the team, the background and motivation, your objectives in terms of what the code will do and how fast it will do it, or how you're going to improve it. Your design overview, what technologies are you going to use from this class, or other technologies if you want to branch out. and the particularly how are you going to leverage parallelism? How are you going to verify that it works? I mean, parallelism, it's very easy to write the wrong answer quickly. And then some administrative things, schedule, milestones, division of work amongst the team members. All right, we'll go over each of these. Team members, 2 to 3 people. 1 or 4 people with special dispensation. I'm not that motivated to provide these without very good reason. There are a couple people who are remote in the class, actually. They have at least the start of a good reason. If there's some other thing that, I really want to work on this problem, but because of NDA reasons, I can't work with someone else, things like that, talk to me. But we would much prefer 2 to 3 people, okay? If you do 3 people, your project should be more difficult. We will expect more from you, so it's going to scale with the number of people you have. Spend some time thinking about why, and if you're going to tackle a particular problem because you're interested in it, do some reading online. Go to Google Scholar and see what's been published recently about whatever you want to do, sequence analysis, you want to do text analysis with latent Dirichlet allocation. You've heard about something else in some other class. Do a little bit of digging in the research and what's going on in the field. You don't have to do cutting-edge research. You don't have to do even dull-edge research here. You can repeat something that's been done. But I want you to know what the sort of scope of the problem is, where it's interesting, where parallelism has been applied. And it is fine to repeat work. If someone else has written a paper saying, here's how we apply parallelism to this particular machine learning problem or something like this, you can propose, I want to re-implement this. That's fine. People do that all the time with algorithms, and someone has some code that's been written in MATLAB, it's a really great algorithm, whatever. They just copy it or they translate it into some other language, C and Python, Scala, whatever, to make it useful to other people, and that's fine. The point here is to demonstrate that you know how to use parallelism, that you can interpret a paper that talks about, oh, we use this parallel technique, where you do sharing of this data with this technique, where do you need to use locks, things like this. These are low-level details that you'll need to implement if you repeat that work, and that's fine. So don't be too concerned about something awesome. Do something useful for demonstrating that you've learned something in the class, and also to help you reinforce what you have learned in the class, okay? So it should just be proof that you know what you're doing in here. As part of your objectives, you should be explicit about what your objectives with the final project are. What will it do? What is the functional aspect of the code? What problem does it solve? What computation does it perform? What are the inputs and outputs that your project will take? What is a must-have feature? What does it have to do? What are optional features that, if you have the time, you're able to put in, or that are speculative, right? There might be, oh, we think we can achieve this. We're not sure that that will work, but we'll try. List those. Performance. I mean, this class is all about taking something that was slow, or taking a serial implementation and leveraging parallel computation to make it faster. How fast will it be? What are your goals here? How fast is it in serial form? If the functionality is just, we already have something that works at this speed, what do you expect it will do later? What sort of parallelism can you leverage on the CPU, on the GPU, across multiple machines? What sort of empirical performance do you expect, and what sort of scale will it come in at, right? Are you trying to achieve something that's not real time, that's, maybe it's interactive rates right now, but you want to get it up to 60 frames a second of video analysis, or you want to take something that takes days and push it down to just a coffee break, right? Are you going to be running some analysis that takes so long, it would take months without parallelism, but you're going to leverage 30 machines or something in the Odyssey queue or on Amazon or something like that, and you're going to try and trim it down to days. These are all reasonable, but be clear about what you're trying to achieve. Like, what are your goals here? Okay? So then give us some details about the sort of low-level implementation. Explain what technologies from class or from out of class you want to use. And it's fine to talk about, okay, we're going to use extensions of Spark, we're going to use the machine learning library or the GraphX or whatever. You do need to explain, however, where the parallelism comes from and what you're going to do. You do have to do some work in the parallelism domain, not just leverage other people's parallel frameworks that are, for the machine learning where, the machine learning in Spark, you can just hand it a very large data set. There's very little work for you in terms of actual parallelism. So you need to explain where is the parallelism in the algorithm or problem that you're solving and how you're going to apply what you've learned in the class to take advantage of that. Finally, verification. How will you demonstrate that your code is working correctly? Do you have existing data? Do you have a serial implementation you can refer to? Do you have someone else's serial implementation you can refer to? Is it a known problem where, or do you have small data sets where it's easy to calculate what should happen and you can prove that or you can at least show that your code works on these smaller test sets? You should have at least 3 milestones. Make them as concrete as possible. This level of functionality, not just we'll have done the background reading or something by the first week. You have 1 month basically to do this. So basically a milestone a week. So 3 milestones. And you'll have an assigned TF who will be helping you through this project. You'll have to meet with them at least once. We'll probably ask you to send them weekly updates around the milestone date, saying, have you achieved it? What's going on? Have you missed something? How are you going to catch up? If you're ahead, what are you going to, not necessarily what are you going to add on, but just tell us where you are. And you'll have to meet at least once in the middle. If your milestone reports aren't very good, then you'll meet more often. And your TF will be unhappy because they have to go to meetings or extra meetings. This is important. Who does what? You're going to be multiple teams. How are you going to, you're entering into sort of an agreement with your peers to work on something. Who's going to do which part? This is very good, even if it's, your best of friends, to lay out, I'm going to do this, you're going to do that. Make sure everyone agrees and understands what the goals are and how the division of labor is going to be set out. And you're responsible for keeping each other on task and helping out when it's needed. Groups are graded together on the final project, except in extreme cases. If there are problems, you need to talk to us soon. If you talk to us at the end, it's already too late, right? We need to know beforehand, which means you also have to be involved enough and paying attention to know that if someone else is slacking off horribly, that you're aware of it. So do be aware of, just be in communication, be honest. If you're on a team and you're not able to produce what is needed for for one of the weeks, or you're falling behind, let your team members know early. Say, I need some help with this, or I don't understand what to do here. Much better than just slacking off and disappearing, okay? So hopefully that won't be a problem. As long as you guys keep in contact with each other and with your TFs, it shouldn't be too much of an issue. All right, before we go on to OpenCL, questions about final projects? Homework 3 will probably be due so it'll go out on the 2nd or so. It'll be due probably around the 16th. It won't be that long. I think it's only 3 problems. It shouldn't be too bad. We've scaled it back because we don't want it to overlap too much with this. It's enough to get you familiar with GPUs and to work with them and deal with OpenCL. Enough that you could use it as a basis for doing OpenCL based project or something like this. So, but it shouldn't be too bad. If it turns out to be another homework 1 problem 5 sort of thing will scale back dynamically. Okay, but we think we've avoided that. Other questions? Has everyone looked at the project requirements? I didn't talk about them here. I'll talk about that more later, but.
Do we have to make a website for the project?
So do we have to make a website? Yes, you should do a web page. That could just be a GitHub IO page. That might be the easiest thing. Just an overview of what you've done. And then there's also a screencast. That may not make sense for all projects. If you want to do something other than a screencast to demo your project, then contact us and propose another way of showing this. But even if it's just talking through the algorithm and the results while you over plots, that's fine. Think of it as not necessarily a demo of the project, but a miniature conference talk on some work you've done, right? That's perfectly fine. Here's the algorithm that we optimized using these techniques. It doesn't have to be long. It should be a web page, probably a screencast or recorded talk about the lecture or about the work. I encourage you to look at the projects page on the homepage to get an idea of what you'll have to do. But there are a couple things there. Any other questions about final projects? Okay. So OpenCL, some more information. Getting platform and device info. So this is so platforms are just what OpenCL engines exist on the hardware that you run this on. When you get that, you might get multiple platforms back. If you look at, so it's worth pulling open that repository, the intro to Odyssey test.py, because this is basically all used in there anyway. When you call OpenCL get platforms, you might get multiple platforms back if you have multiple OpenCL installations. You might have Apple installed and Intel installed, and so each of them can target the hardware. And you can check the name, the vendor, the version, and then you can get devices. And that's where you get a list of GPUs, CPUs. Depending on what machine it is, it'll have somewhere between 1 for the CPU and 3 if it's got integrated graphics and a GPU or multiple GPUs. And each device then has a name, it has a type. You can turn that into something interpretable with this call. Clock frequency, and then things you might actually care more about. How much memory can you allocate? What is the maximum work group size? This will be multidimensional. No, this is a scalar. How many dimensions of a problem can you solve? Minimum is 3 enforced by the specification, but it could be as high as 4 if you were doing tensor, if it supported tensor sort of behavior. I don't think any hardware does yet. And then the maximum work item sizes, which is what is the largest dimension of a group that you can send down. Often on a CPU, if you're doing OpenCL programming and you're targeting the CPU, this may only be a one-dimensional thing. It may be that the size, well, let me show you some actual numbers. So this is on my laptop. So it's got one platform. It's just got the Apple OpenCL installation. 2 devices, the CPU and the GPU. So this is that conversion to string thing, GPU versus CPU. You can see the maximum workgroup size is 512 on my GPU, 1024 on the CPU. The maximum work item size on my GPU is I can put 512 in any of, the product of these has to be less than 512. So I can make a group of any dimension up to 512 in X, Y, or Z, but I can't go above 512 in their product. On the CPU, it's a little more constrained. I can only have a one-dimensional vector. I can't do 2D work groups. So if I were doing image processing on the CPU, it would be highly constrained in terms of what I was able to do. And I should be aware of that is the main thing. That I'm not going to get, when I try to optimize for a work group of, if I'm doing image processing, I probably want a square template of workers. I don't get that on the CPU. Anyway, if you're doing something with OpenCL, if you're doing more stuff, you'll have to start digging into this if you're going to do an OpenCL final project, you'll want to be aware. You may be targeting just a specific hardware platform. You might be working, I'm just going to work on an NVIDIA K20 like they have on the cluster, K40, whatever is there. And then you'll just want to get this at the beginning and then optimize towards it. But if you're writing general OpenCL code, it's more tricky. Yes?
For a given set of hardware, how good is OpenCL at optimizing for it?
For a given set of hardware, how good is OpenCL? It really depends on the vendor.
Okay.
So NVIDIA, I believe the performance hit is about, you get about 70% of the performance you would from CUDA. I don't think that that's necessary. I think it's just that they spend their engineering effort on CUDA more than on OpenCL, and I think it's getting better. Apple is doing crazy things with this Vulkan? No, not Vulkan. Metal. Which is their sort of OpenCL competitor or something like it. So they probably won't keep improving. So they're responsible for OpenCL on their own platform and using, and it's Apple's OpenCL implementation that's targeting this GPU. And they're probably not going to push beyond 1.2 rather than OpenCL is at 2.0 and things like this. So it's possible that in the Apple space, because of corporate politics, that it won't be very good compared to what could be there. NVIDIA is pretty supporting of OpenCL. So I don't think that there's that much of a problem targeting that. So AMD is, I think, pretty strongly behind it. I think basically the AMD ATI maybe as well. If it's basically the second, not the market leader, but the next one back, expect their OpenCL implementation to be really as close to good, they'll probably spend time on it because they get more benefit than the market leaders like NVIDIA who, almost all GPU code is in CUDA, and so there isn't as much of a push. Apple doing its crazy stuff. So expect things from like AMD and something like that to be pretty good. All right. I want to talk about image processing some more, especially setting up and dealing with buffers. Because, well, homework 3 will have a couple of image processing-based problems, and you'll have to deal with this local memory halo thing. I don't mean this kind of halo, I mean something else. All right, so if you want to pull open this, I just pushed this morning, the OpenCL examples, there's a load halo.cl. It's just the setup code for this problem. All right, we have some local computation over, almost all image processing is local. You have a pixel, it has a neighborhood, you compute some new pixel, especially if you're producing a new image, you produce some new value at some central pixel based on its neighborhood of inputs. So for example, the blue output pixel here needs the red input window to compute its output. Like we talked about last time, we don't want to go to global memory multiple times. That would be, we would read every input pixel. This is a 5x5 window. We'd read every input pixel 25 times because, we'd read this pixel for this one, but then also this output pixel is going to read this one, and this output pixel is going to read that input. So 25 times slower than we need to be. And memory accesses are slow. We don't have any sort of cache. Well, we don't have any sort of automatic cache. So we have to do our own caching here. So we copy that. We do that by copying into a buffer in local memory. All right. Our work group, you see our friends that we can synchronize with and cooperate with, is the green square. It's the 4x4 work group. And we have typically, one thread or work item in OpenCL parlance per output pixel. So with this work group, how large does the local buffer need to be if we're doing a 5x5 input window? Anyone? What? 5x5 or the 4x4? Well, for our work group, let's talk about the local buffer that we're going to copy into. So we've got a 4x4 input, or we've got a 4x4 work group. Each thread in that work group needs a 5x5 region. What's the size of our buffer, n by n? Well, no, 5 by 5 per pixel. But now I'm just talking about the shared workspace we're going to allocate. I should have drawn it. Well, no, then you could just count. Thirds times 60. What's that? Sorry? 10 to the 4th. That would be the number of reads. I think that's, so this is the size of the buffer, right? Because we need every pixel to have its 5 by 5 region around it. Okay, so it's going to be our workgroup size in one dimension, plus the input size in one dimension. Chop off 1 because central pixel, and divide by 2. So the 5 by 5, we basically have to take we've got our central workgroup, and then we add 2 over here and 2 over here. Oh, it shouldn't be divided by 2. Hold on, let me fix that so it doesn't bother me for the rest of the, sorry. Workgroup size plus our input size minus 1, because we have the central pixel, so we drop 1, and then every pixel needs some extra boundary around it. Okay. So these are the halo. I'm going to hammer on this because this is the term you'll see. The halo are all the pixels that don't correspond to an output, one of the threads directly, right? We're going to compute all these pixels for whatever filtering or other computation we're doing and write them to the output only within the core. But we need, for the input, some larger box. How do we get this from global to local memory? Okay, remember, coalesced reads are good. Coalesced reads are when we read contiguous memory elements with contiguous threads. Contiguous just means in my work group, these 2 threads are contiguous, these 2 are contiguous. These 2 are probably contiguous, although it might go in the other direction, but usually across X, the same direction that memory goes. So if this one reads a memory location, and this one reads a memory location right next to it, especially on GPUs, we probably pay 1/32 the cost of a memory read if we bundle those all together. Right? If each one of these did a read independently, it would take a long time. They'd be serialized, they would wait a great deal. But if 32 of them in a row read the same memory block of 32 values, you get it back in the same cost as one memory read. One serialized memory read. So what we do is, this is not my latest slides. It should be 0 indexed. What we do is we take and we get a linear index for each thread, and then each thread is responsible for reading 1 row. And then we just loop over the rows in our full buffer, reading the global memory into the local memory. Okay, so I had broken this up and then I don't know where my slides went, but is it clear how, so these are our work group. We have 16 threads in the work group. And so we just don't treat them as a work group, just treat them as a list of indices. And then we assign basically each thread the task of fetching 1 memory location from the input, the gray one, into the red local buffer. And we do a row at a time. All right, so we're reading 1 row, 1 coalesced row per loop iteration.
So to clarify, in the empty thing, the stuff is green is the work group. Each one has a thread, and each thread in the red box is your halo.
The red box is the buffer. Yeah, I'm gonna, hammer on this. So our work group is green, yes, correct. The halo is just the part outside, the part of the input that we need from outside our local. The red is the local buffer, the buffer that we're going to use, which includes the core and the halo.
Yeah, so the halo is the red.
Right. And yeah, so we have 16 threads in our work group in this case. Yes, this is all just to set up before compute. This will make the computation much simpler because it will just operate on the red. And the other thing is, once we get it set up, I'll show this. Once we get it set up, we don't have to worry about boundary conditions anymore in our computation. I talked last time about how our computation, the sort of core of filtering or whatever we do, tends to be complex. And so if we put more complexity in there, in terms of dealing with boundary conditions and things like this, then we're adding complexity to complexity, and bugs tend to grow as sort of complexity squared, right? So, because of just interactions between parts. So we try to keep our core algorithm clean, right? So that once we have this halo, no one has to worry about boundaries. Everyone just looks at the data around them. Oh yeah, so the preprocessing, there are only 8 threads working. Because, right, we have this, they're all technically able to read more data, but we mask them off. The same way that when we do, we check for valid inputs, right? We say, just go to sleep. You know, we have this if the X and Y are within the bounds. Same thing here. Here's a question, is that a problem? What are we losing from that? What are we giving up? Basically, we've got idle threads, right? This is always bad, almost always bad. Is it bad in this case? Oh, have 9 through 16 read the next row? How much faster or slower is this? Is that going to be faster? Is it? Is it twice faster? Memory reads are serialized, yeah? So what's going to happen is the first read's going to execute. And this thread, right, we have multiple threads on back to the picture of the compute engine, right? We've got a bunch of threads, a bunch of contexts, and a bunch of things. And the idea is when one of them is busy waiting for memory, other ones can run. So if we were to have 1 through 8 reading the first row and 9 through 16 reading the second row, those are separate memory reads, right? Because they're separated by the width of the image. So they're probably actually far apart in memory. So 1 through 8 executes its memory read, and the thread goes to sleep. And some other thread switches in very quickly and uses the compute hardware, right? Versus, we do it this way, goes to sleep, and then we read the next row. It's basically the same and with simpler code probably here. It might be slightly faster because you won't have a little bit of compute there before it initiates another read. But you're going to also remember you add to the when you add to your computation, when you make it more complex, the context size goes up, right? You need more registers to store what you're doing and keep track. So you could actually reduce the number of threads that are live on the hardware at any one time, and by using just more complex algorithms. As opposed to, if we were to do, if we were to try to put the second block, second half of the threads in here, it's the same coalesced, right? Because these are going to be separate reads, right? Coalesced reads basically you divide by however many threads you can get into that, up to 32. Into that coalesced read. Since they're going to be serialized anyway, the first row and the second row, let me bring up the second row. They're going to be serialized anyway, so it doesn't really matter which threads read them. If it's the first ones, because there's just a little bit of computation in there, right? There's going to be a coalesced read of 8, and then a coalesced write where they write to the local buffer. It's not even coalesced because it's on-chip memory. And then the next, and so there's a very little bit of computation before it goes to the next row. So coalescing is basically the same. These two reads can't be coalesced because they're, right, the image could extend very far, and in general would, right? So the memory location being read by the first row is very far away from the second row. So that's where the drawing starts to break down because they're talking about 3 different spaces, and I don't have this real estate to show it. They do. This is just where they land in the, so our root group and where we're going to output, only where we're going to output relative to the image input. I'm assuming the input image and the output image are the same size. The work group is this green square, laid out in 2D, because we're working in images. And so it's a 2D work group size, a 4 by 4. I convert that index to 2D coordinate, or to a 1D linear coordinate, just to give them a number. And hopefully a number that matches their thread, the linear index of the thread in the hardware itself. And then I just use those numbers to assign who's going to work on this column. But this is not where the actual data is. They are going to fetch that data next. They're going to go down all the way and fetch into the local buffer, which is the red. Right? We have different pieces here, unfortunately. It's going to be separated like this. Right, we have our full image. And we have some subregion that's where we're going to work. Right, this is the core. And in this case, it's 4 by 4. That's just the output we're computing here. We're going to have a thread per output pixel. Okay. We have then also over here our local buffer, which is 8 by 8, right? Because the core plus 2 on each side. And so let me erase the core in here because it doesn't actually matter so much. We're going to read the rows here. Threads 1 through 8. We'll read this row, and then 1 through 8 here, and then 1 through 8. So this is all done by thread 1. Just the setup part. Okay. Does that answer your question? So they're drawn over each other in the slide, but they're separate pieces. And then after this, okay, we have the local buffer, and we have some pixel within this central region, which corresponds to the output, the core. And now its entire computation, it needs this 5 by 5 region. It's all in the local buffer. There's no worries about am I inside or outside right here. Am I inside or outside the input image? Anything like that. It's just, I know that I have values. I know that they're all valid for my computation. I can just fetch them without worrying about boundaries or anything like that. So it simplifies the code when we get to here. We compute all of these values, right, with fairly simple code. And then we go back here and say, okay, we write it to this position in the output image. Or maybe in the input image if we're doing in place, but then you get into locking problems. Does that answer? Is that clear? What if instead of fetching the columns, you mean, so we fetched, so you mean so thread 1 fetches a column, but over multiple iterations. So you're saying what if we fetched this order, so thread 1 read this one, and thread 2 read this one? Right. It's not coalesced if thread 1 does it. So that would require a loop, right? We're going to loop over rows or columns, yes? If we do it this way, so coalesced read is when we have a bunch of threads reading a bunch of threads simultaneously reading adjacent memory. So if we do it in this direction, the memory is adjacent, right? Because the layout direction is this way. So thread 1 fetches this one, thread 2 fetches, thread 1 fetches that one, 2, 3, 4, 5. So that's coalesced. If we do it this way, then thread 1 fetches that value, thread 2 fetches that value, which is far away in memory. Right? The separation between this pixel and this pixel in memory is the width of the image. So that's not coalesced anymore. That's sort of anti-coalesced. Right? Because what's going to happen is now thread 1 is going to pay the price here for fetching 32 elements. GPU memory is like that. You ask for 1 and you get, it's like a cache line without the cache. You get 64 back. And whether you use all of it or not is up to you. So thread 1 is going to basically read the entire thing. And then thread 2 is going to read the entire, a large block. And then thread 3. And then you'll move to the next column and do it all again.
I'm very confused.
So let's see. They are the same threads. They're organized in 2D, but that's just a numbering convention, right? They have some global ID. They have some local ID that might be 1 or 2 dimensional. Or in this case, it's 2 dimensional. That's just a convention. That's just to make it easy for the programmer. We can convert that from row column to a linear index in this way, right? The same, right? And then we just need to use them to load rows. So yes, the code, right there are 16 threads running. And then they hit this maybe some code. Actually, let me bring up code for part of this. That'll be easier. All right. Oops. Go full screen. All right, so this is, we've got an image, we've got an output, we've got a buffer, we've got an image width and height, and a buffer width and height that we've already computed as, you know, whatever our local workgroup size is plus our halo, and we've got the halo size. So we get our position of the output pixel, that's just our x and y from the global ID, yeah? So we've got some image. It is width and height, and we have some x, y, okay? And then we get our local position relative to 0, 0 in the work group. So we live in some work group, right? So x, y is right here, and we've got some work group. Our LX, LY is relative to right here. So that's LX, LY. Right? Okay, so that's just the position. All right. Now, we'll need later on for the code, well, we can come back to this. We have some local buffer as well that lives in the same space. Let me try and draw it in the right location, but in a different piece of this board. So here's our core, and our buffer might be this big. Let's say that this corner corresponds to this corner, okay? So we've got some buffer. We've got our core, which we know we live inside. We've got this is our LX, LY, right here. And we are computing this offset now, right? This is, lines all over the place. I want to do a nice drawing of this. I didn't have time, but I will post one. This is buff X. What? And buff Y, right? This is where our coordinates, so we have our thread has a bunch of coordinates, right? It's relative to a whole bunch of places. It's relative to, this is the GX, GY base. This is the LX, LY origin. GX, GY origin, LX, LY origin, and buff X, buff Y origin. Right, the last one where the cursor is, right? Because we've got this local memory halo, right? So they're all related through these various, offsets, okay? This is code we're going to give to you. This is why I'm giving you this code, because it is painful to think of all these, and off by 1 errors and things like that. So we have a buffer coordinate, we have a local coordinate, we have our global coordinate, okay? And then we have a 1D index within our work group. That one we do relative to LX, LY and the size of our group, right? Because we have however many threads running in a 2D array. So it's the same image math that we used, that we showed last time, and I think the time before that, we used to get this index 1D, which is basically just our thread index, or a 1D thread index. All right? And then we'll have a couple of variables, and this is it. This is to set up the halo. Once we get all of those coordinates, all the work is, all right, where the hell am I relative to all the things I care about? So the first if statement, is my 1D index smaller than my buffer width? Right? I'm going to load this, I need to load blocks of memory, right, into here. I'm going to do that coalesced read. I have this many threads, but these guys should not do anything. All right, they're not, okay? That's the first if statement. Am I a useful thread at this point? If I am, all right, loop over the rows in my buffer. All right, how many rows do I have in the buffer height? And then your standard image math. You know, the buffer at row times the buffer width plus my 1D index. Fetch from the image. Why not just image of value, blah, blah, blah? Why would I write it this way instead of the much shorter array notation? Can I read that pixel? I cannot read that pixel, right? All of these pixels are invalid. And if I'm up in the upper left corner, all the upper left pixels are invalid. So put in a helper function. It takes the image width and height, and then I need some, you know, the buff corner x index 1D, that's the offset, that's the coordinate here relative to this one, right? They're all just a bunch of spaces. Where do I put the data? Oh, no, I don't need that at all. Sorry. It only needs to be the first, no, that's right. Because buff corner x is, buff corner x is this pixel in this space. See, isn't this clear? Sorry. Buff corner x index plus 1 index 1D is the coordinates in the global image of the upper left corner of the buffer. That's what is computed up above. I need to go back and read my comments. So it's saying fetch this location from the image that is this big. If I'm off the edge of the image, give me back something. That might be a special value that indicates out of image. It might be a repeat. You know, take the closest valid pixel from the image and repeat it. But somehow get me some data into my local buffer that I can use. And then put up a barrier so that all of us get to this point and the local memory is ready. The processing code here now only uses local buff. I confused the projector. Come back. So the processing code right here now, ignoring all of this, now can ignore everything except for what is my location in, I can see it, hold on. Oh no, it crashed. No, okay, good. All right. The processing code now only has to worry about the local buffer. It has its position in the local buffer. It has this coordinate from one of the things, and can just very simply say, okay, well, I know all of my data in this region is valid. The code can be very straightforward. It might have to deal with special signal values for out of bounds, but the computation is fairly straightforward. And then once it gets done and computes the output, it just needs to do it down here, right? I'm assuming that it wrote back the answer into buffer, which may or may not be correct. It might have, instead of some buffer, it might just be output value or something like that. But I just take my global input. I check that I'm actually in a valid region, right? Because I may have been down at the bottom of the image. And I just output it. But the code after that setup is simpler. So this basically turns into boilerplate when you need a halo of a particular size. Yeah, good. 2 in this case, for this code. See? I'll commit that later. So the halo in this case is 2. You had a question as well? All right.
So is it always better to have a square core rather than say if a rectangular one, which you can use one because
Is it always better to have a square core? No, in fact. So it's almost always the case that you'll have a square halo, or you'll have a square input window. I mean, sometimes you'll do you'll have an input filter that requires a strange size, at which point you'd have to split halo here into right? It could be a rectangular input window for some reason, 3 by 5, or the computation the stencil might, yeah, the input relative to a pixel might be 3 by 5 instead of 5 by 5. The green square doesn't have to be square, and in fact, it doesn't. The core could be rectangular, and on some hardware, it may be better to be rectangular. If you were implementing this for CUDA, 32 is the sort of magic number for thread size for optimality, and you can't do very good synchronization. Can't do very good synchronization, or as much, between groups of above 32. And so at that point, you might say, okay, I'll make it 8 by 4. The code here will still work if the halo width is the same on all the sides. Nothing in here assumes a square. You do have some assumptions here about halo size versus core size, because if the halo is too wide, you don't have enough threads to read the whole row, and then it gets more complicated. But that's a strange case. I have a very small input window, and I have a very large, where I have a very small core, a very large input window. I probably want to think of some way to flip my computation to make it so that I'm doing more work, because you're going to read, that means I'm reading a huge amount of data, and I can't be computing that much for that input. So I have a poor memory to compute ratio, right? And I'm going to do a bunch of repeated memory reads across different cores, or across different computation green square cores, right, groups. So when that starts to happen, you should think about maybe there's some other way to solve this. In this one, I think I was saying there's in this one, down at the bottom, I assume that the output was being written to the buffer temporarily. This would probably just actually be some output value coming off of this computation, rather than writing it back to the buffer, because that would require another barrier and things like this. Yeah. Since I didn't have an actual computation here, I just stuck something there that I actually had. So this would actually put something back, but it should just put back, this is a null op, right? This is basically a copy operation with a local buffer for some reason. But you could just put any variable there, right? And it's gonna be valid. All your computation here, even for threads that are outside this valid region for output, will compute from the local buffer. It doesn't cost anything for them to do computations because you're in parallel mode. So it's fine. Not, maybe. Depends on the hardware you're running on. On a machine like NVIDIA, where they're lockstep computations across 16 or 32 threads, then yes, but you can't assume that. So you put in barriers. And you do. But they're not necessarily always, without a barrier here, they won't update at the same time. They're not guaranteed to. What does which do?
the typo, ampersand.
Oh yeah, no, that should be end. Yeah, it's a special secret. All right, we're going to give you this code, but you need to understand it, and sometimes you may need to change it.
But it doesn't run, right?
Doesn't run?
Well, there was a day for it.
Whoa. Like I said, you might have to modify it. I didn't say it was good code, I just said I was going to give it to you. No, it doesn't run. It's cut out of parts of code that did run, and then I threw the part at the bottom. It's extraction from the existing code. All right, so we're out of time. If there are other questions, just catch me after class. I'll post a better drawing of this on Piazza.